I will discuss how to find out the gravitational field due to uniform straight rod. On the first part, we are going to discuss what about the value of gravitational field due to a uniform rod at an axial point. So just consider a uniform rod of mass m and length take it as L, and we are going to find out what about the value of this gravitational field at a point P on its axial line, which is at a distance take it as r from the end. So as it is an extended body, for the calculation purpose we can just consider a small element over here. So if you are taking a small element of mass, take it as dm, and this width of this small element is take it as dx, and this small element is at a distance x from point P. So first we can write what about the value of gravitational field at point P due to this small element of mass dm. So if I am just representing it as dg, that we can write it as it is g dm divided by x square. So you can write the value of this dg is equal to g into this dm is represents the mass of this small element, that we can take it as total mass m divided by total length L into length of that small portion, which is dx, divided by x square. And if you'd like to find out the value of total gravitational field at point P, we can go for integration of gm divided by x into 1 by x square dx, and we can put the limit from over here. You can observe that the value of x is changing from r to r plus L. So we can write this g is equal to gm divided by L into this x square, we can take it as x raised to minus 2 dx, and integration of this from r to r plus L. So we can write this as gm divided by L into x raised to minus 2 plus 1, that is x raised to minus 1 by minus 1, and limit is changing from r to r plus L. So if we are putting the limit, we will get the value of g is equal to gm divided by L into 1 by r plus L minus 1 divided by r, if we are putting the limit. So you can write it as gm divided by L into r minus L minus r divided by r plus r into r. Or you can write the value of this g is equal to gm divided by L into L divided by L plus r into r. Or you can write the value of g is equal to gm divided by r plus L into 1 divided by r will be the value of gravitational field at a distance r from the end of the rod. Now in the next part, we'll discuss how to find out the value of gravitational field due to a uniform rod at an equatorial point. So let's say our aim is to find out what about the value of gravitational field at point P over here on the equatorial line. So same as like in the previous case, we'll just consider a small element over here. Let's say that small element is at a distance x from the center, and consider that this mass of this small element is dm, and we know that this gravitational field due to this dm at point P is directed towards this point, and let's say this gravitational field due to this small element is represented by dg, and a distance of point P from the center is represented by take it as r. So first we can find out the value of gravitational field at point P due to this small element of mass dm, which is represented by dg over here. So dg we can take it as nothing but g into dm divided by, from Pythagoras theorem we can write this distance is going to be under root of r square plus x square. So we can write it as r square plus x square the whole square, that is r square plus x square. And let's say this is making some angle theta with respect to the vertical. So if this angle is equal to theta, we can resolve this dg into two components. One is along this direction, thus we can take it as nothing but dg cos theta, and we can take it as another component of force along this direction, which we can take it as dg sine theta. Similar to this, if we are considering another element over here which is at the same distance x from the center, let's say this distance is x, so we can say that again this element will also exert a gravitational force dg, and again if this angle is equal to theta, again we can resolve this one into two components, that is dg cos theta and this component is dg sine theta. And you can observe that these two components are going to get cancel each other, so the net gravitational field is already due to this dg cos theta. So we can write the value of net gravitational field as gravitational field at that point, that is g dm divided by r square plus x square into the cos component of it, so we can write into cos theta. So we can write this dg is equal to g dm divided by r square plus x square into the value of cos theta. From the triangle we can write cos theta is r divided by under root of r square plus x square, or you can write this dg is equal to nothing but g dm into r divided by r square plus x square raised to 3 by 2. And if you like to find out the value of net gravitational field, so you can write it as integration of all these dg cos theta component, that is integration of g dm into r divided by r square plus x square raised to 3 by 2. We can write the value of this dm in terms of m, that is m divided by total mass by total length into length of that small portion x into r divided by r square plus x square raised to 3 by 2. And we can put the limit, as you can observe that the value of this x is changing from minus L by 2 to plus L by 2, as the total length of this rod is L. So we can put the limit from minus L by 2 to plus L by 2. We can write the value of net gravitational field will be equal to gm into r divided by L into integration of 1 divided by r square plus x square raised to 3 by 2, and the limit is changing from minus L by 2 to plus L by 2. To integrate this function, we can take it as this x is equal to r tan theta. So we can write the value of net gravitational field as gmr divided by L into integration of 1 divided by this, we can take it as r square plus x square, we can take it as r square tan square theta into raised to 3 by 2. So we can write this is equal to gmr divided by L into, we can take this r square as common, so it becomes equal to r cube on denominator into dx divided by 1 plus tan square theta raised to 3 by 2. So this becomes gmr divided by L into r cube, and instead of dx, because we just consider the value of x is equal to r tan theta, so we can write this dx is equal to r sec square theta into d theta. So if you are putting this value instead of this dx, so we can write it as r sec square theta d theta divided by 1 plus tan square theta, we can take it as sec square theta raised to 3 by 2, that becomes equal to sec cube theta. Now if you are cancelling these terms, like this r and this r square over here get cancelled, and this sec theta and sec cube theta over here get cancelled, so the remaining terms we can write it is nothing but gm divided by lr into integration of 1 by sec theta, we can take it as cos theta d theta. That the value of this integration of cos theta is nothing but sin theta. Now we can put the limit which is taken from minus L by 2 to plus L by 2. So to substitute the limit, we can write sin theta in terms of our variable. If we are putting the value sin theta in terms of x, we can write it as x divided by under root of x square plus r square, and the limit is changing from minus L by 2 to plus L by 2. If we are putting the limit, we'll get as it is gm divided by lr into L by 2 divided by under root of L square by 4 plus r square minus L by 2 divided by under root of L square by 4 plus r square. So this negative becomes plus, so we can reduce 2 times of this particular value. Now if you are calculating it, you will get the answer as nothing but 2gm divided by r into under root of L square plus 4r square. So this will be the equation for a gravitational field due to a uniform rod at its equatorial point.